All right, now we're ready to see what it takes to parallelize loop 3, the third loop around the microkernel. And just like before, what we want to do is search for OMP, let's see, that pragma, there it is, in routine loop 2. So what we will do is erase it there and move it up into loop 3 and save that into the routine gemmmt loop 3 mr by nr kernel.c. And then we go to the terminal session and we double check that we still have 4 threads set. And we don't. Ooh. So we better set them. Export OMP num threads equals 4. Now we're in good shape. And then we make and execute mt loop 3 8x6 kernel. And it compiles and then it executes. That was pretty quick again, so we're probably doing okay. But we really should check whether we are getting the right answer. And it's pretty obvious that we are not. At least not once the problem size is bigger than 48 by 48. So what's going on here? Well, if you think back about the picture that describes the 5 loops, what do you notice? Think about it for a second. What might be going wrong here? Here's the implementation. Have a good look. You may even want to pause here. All right, so what's wrong here? What's wrong is that we only allocate space for one block A tilde. And if we now parallelize this loop, then what you end up with are many threads packing different parts of the column panel of A into the same temporary space A tilde. And what we really need to do is create a space for each of these blocks, one per thread. So how do we fix this? Well, notice that we need a buffer A tilde for each thread that is going to be executing in parallel. So what we want to do over here is multiply the amount of space we allocate for A tilde by the maximum number of threads that we may encounter. OMP get max threads. So now we are reserving more space. And then down here, once we start executing the loop, a specific thread should use only part of that buffer. And the part that it should use can start at, let's see, each of these blocks is MC times KC doubles. And then we want to multiply that times the thread ID. To get to the space that we want to use for this particular thread. And then what we want to do once we have packed into that particular space is use that to pass down to routine loop 2. And with a little bit of luck, this fixes our problem. Let's double check that we still have the right number of threads. We do. And then we can say make, the usual. And it compiles. And it executes. And there it is. And notice now that we are actually getting the right answer. So this solved our problem. So now let's go and have a look at what this does to the performance. And once again, let's have a look here. And Now let's choose to also show the performance for the multi-threaded loop 3. And if we go to the bottom, this is the graph that we had so far. And if we hit run, then we get this graph right here. And what we notice is that parallelizing loop 3 performs better, but it gets this funny zigzag. Now, where does that funny zigzag come from? Well, we'll discuss that in a separate video, and that may then also give you some ideas of how you may be able to fix that zigzag. For now, we'll just live with this.